Next topic, we'll talk about carbon measurement for mitigating climate change and will be delivered by Rebecca Hood-Nowotny, Ph.D. from the University of Natural Resources and Life Science, Vienna, BOKU. This session will be led by our moderator, a lecturer from the Department of Agricultural and Biosystem Engineering. He is Ahdiar Fikri Maulana, Ph.D. Let me read the moderator's CV for you. So this is the CV our moderator for discussion today. The moderator in the last session today is Ahdiar Fikri Maulana, PhD. The last education is PhD in Plant Nutrition and Soil Science, UGAS Iwet University. And one of research project is isolation and characterization of endophytic fungi and their role in the propagation of Ficus fistulosa seedling. Don't have to wait any longer. Ahdiar Fikri Maulana, PhD, the time is yours.
Thank you. Thank you for the time, for the opportunity. Good morning. Is it morning now?
Yeah, it's morning in Austria.
Morning in Austria, actually. Yeah, good afternoon for every participants, be online or even offline. This is the second session. Actually, we will have a presentation by Dr. Hood-Nowotny about the carbon measurement for mitigating the climate change. So from the first session, which is fecal microbiota, it is a bit far. Dr. Hood-Nowotny. The previous session, we talk about the fecal microbiota. So, and then in this session, yes, we will have your carbon measurement for climate change, I think. And then we will have a long sessions, just like Dr. Hood-Nowotny said before. Again, thank you on behalf of the organizer. I think thank you for agreeing to our invitation to become a speaker to our event, the 6 summer course. And then even though it isn't on Sunday, it is a holiday for you, I think. And then Dr. Hood-Nowotny is already present here. And MC, can you show us the CV of Dr. Hood-Nowotny first, maybe?
Oh, I'm not sure I supplied it, actually. Or did you get one?
I think they have it.
Uh-huh. No?
Okay. Oops. Sure, we have it.
It's when it's cold in Austria.
Oops. Okay. So Dr. Hood-Nowotny is working on the soil, especially carbon in soils. And then she took the PhD in soil science in the University of Reading. And she has many publications here. The latest is about carbon allocation in cassava. Is affected by water deficit and potassium application A13C CO2 pulse labeling assessment. And she has many research project, generation legume to wood nitrogen climate. So we can ask many questions, I think, for Dr. Hood-Nowotny. I think without further ado, we will have your presentation for 100 minutes, and then we will continue. And then we will continue to discussion.
Bit of a marathon.
Marathon, yes.
Yeah.
So I think we can start now. Dr. Hood-Nowotny, the time is yours.
Okay, can you see my screen?
Not yet. Can you share it once more?
Do I have to share it again? Oh, okay. because I can see it.
Okay, it's on.
It's full screen, is it?
It's clear to me. Yes. Thank you so
Yeah,
much.
yeah. Perfect. Thank you. Thank you, everyone. I'm delighted to be here on a Sunday morning. I was really enjoying the videos before we started the session. They were really lovely. And I don't know how I follow them up actually, so I haven't got any fire to throw or dragons to show, but hopefully I'll keep you entertained or do a bit of edutainment for the next 100 minutes. So yeah, and Andia said, I'm Rebecca Hood-Nowotny. I work at the BOKU. This is the building where we work. This is in Tulln, which is about 40 kilometers north of Vienna. It's part of the BOKU, and I'm in the Department for Soil Research. So today I'm going to talk about soil health regeneration and soil carbon and building up soil carbon in the soils and how we measure it. So the whole thing about regeneration or the whole rationale for regenerating soil health is it's got the potential to improve environmental and ecological issues at a very large scale, and especially, I think, in Indonesia, regeneration of soil health in palm oil production would be a really cool thing to do. Basically, because you've got so much palm oil in Indonesia, it's one of those things. But other processes and other agricultural systems also are really in need of regeneration and improvements in soil health. Yeah, one of the other reasons is that, basically harvesting, pruning, weeding, and fertilization are dominant activities in systems and plantations, and they're activities that really the soil, in the sort of like the long history of soil, they've never really had to cope with before. And so we hypothesize that there's a trade-off between higher intensity management and ecosystem function provision and biodiversity. So basically, the more intensely we apply fertilizers, we plow, the less biodiversity and ecosystem function that there is in the soil. So we've got to be careful with our soil. We've got to make sure we feed our soil and take care of our soil. As I said, in the past, in the history, when we look at the history of soils, in the past, we just had, in the very distant past, before agriculture, so before 10,000 years ago or whatever, soils, we didn't have monocultures. We always had, very rarely had monocultures. We usually had large mixtures, although fertilization was done by the animals and the general turnover. It was very, very low, really. It was very low amounts of nitrogen and phosphorus going into the systems, probably about sort of less than 50 kilos a hectare. And then obviously we didn't have the pesticides and chemical controls that we have today. This slide's a bit of a leftover, but so sorry. I've just got a thing about different oils here and different production of oils in terms of hectares used. So what you can see here is that you can see soybean, the number of hectares that soybean takes is what palm oil takes. And so this is why it's quite interesting to think about palm oil and why Indonesia obviously is doing so well. But I'm not an advocate for palm oil per se, but it was just quite an interesting statistic left over. And we have big changes worldwide with the soils. Soils have to undergo enormous changes in the next few years. We have climate getting warmer, and you can see this little scarf diagram which shows the anomaly here. This is it's a really nice visual to show how much the temperature has warmed. This one is for Austria, so you can see over the past sort of 300 years how much every year that mean temperature of the the difference between this year's temperature and the mean temperature of the past 10 years changes. And so the redder it is, the hotter it gets. And we can see that really, really strongly. We saw a couple of years ago with the really high temperatures in Paris. This isn't people celebrating their Olympic wins. This is people trying to cool off in Paris. I think it was 2022 or 2021. We have a lot of wildfires and things like that. And it isn't just the fact that we have a warmer climate, it's also that we have far more unpredictability in the climate. So we can't really say when the rains are coming often. There's all sorts of funny things happening. I mean, we know I've recently been in Chile and they were saying they used to have 3 months snow. They now have 3 weeks of snow. I was also in Morocco and they were saying they used to have 900 millimeters of rainfall, or no, 600 millimeters of rainfall from from October to December. And now that rainfall is 300 millimeters. So we've got these huge changes in weather and weather patterns, and so which we just can't predict. And so we need to build resilient systems that can cope with these massive changes. And also on top of that, we have demographic changes. You might have noticed not many people want to be farmers these days, and this is really quite an important shift. People want to be researchers, they want to be computer analysts, and so there's a big push against farming. But also, if you see this graph in the bottom left-hand corner, you can see that population is actually decreasing in Indonesia, and that means that there will be less people for doing production in the future. So they're just sort of it's just a bit of background for you to take on when we're thinking of these issues of soil. Well, the foundations of soil as a soil health is understanding that soil is a living entity. I mean, the soil is a soil that's not living is basically dust. And often they'll talk about, I mean, a lot of people talk about soil on Mars and things like this, but because we don't believe there's life on Mars, I would argue that there's no soil on Mars. And soil, to be defined as a soil, I think needs to be defined as a living entity. And soil provides protection, diversity, and carbon and nutrients. And that protection, diversity, and carbon nutrients provide us with resistance, resilience, and sustenance. So the soil is it acts as a buffer to many of the problems that we have. And many of the climate change problems although it's a very thin layer, I mean, there's some nice films recently called 4 Inches of Earth or something, 4 inches of soil, etc. Is a very, very thin layer often, the layer of soil. I shouldn't say inches, should I? I should say 15 centimeters of soil. But it's a very thin layer, but an incredibly important layer in terms of the exchange of greenhouse gases globally, etc. And so if we look at soil carbon ranges from we can go up really to 45% of the soil mass can be soil carbon, can be SOM, soil organic matter, or soil carbon, SOC. And although the term humus, soil, I prefer to use the term soil organic matter, but in this diagram, we have humus, which is the same thing as soil organic matter. That humus fraction, that's the soil organic matter fraction is, or the soil organic carbon fraction, is made up of some very recalcitrant material that's not easily degraded by the microorganisms, or it's just there. It's just sort of fairly inert and there. And then we have usually in a fairly large proportion of that, about 5% of that is what we call the soil microbial biomass. And then about 10% of that is roots. And usually the soil microbial biomass is about 1.2% of the total soil organic carbon. The soil organic carbon that's there provides a wealth of different, it really provides a wealth of different processes and different benefits to the soil. And as I go through, we'll see some of those. So just to give you a bit of an idea of, I could do, yeah, maybe it would be good to do this. I'll often do a visioning exercise here with my students, because I think it's quite nice to do. So we here in the soil we have lots of different organisms, and we have different soils. Obviously, have different soil textures. So we have sands that are really big. If they're really big particles, you can see here on the right-hand side of the more complex diagram, that sort of the right-hand side represents a fine sand of greater than 200 millimeters. You see on the left, there's the clay of about 2 microns, and then in between you see the silts for about 60 microns. So obviously different textures will give you different amounts of microbial biomass. Also with the clays are they're often very, very layered. So we have these really sort of like fine layers of clay, where sort of you can get hyphal intrusion from fungi and stuff that makes it that means that other things such as amoeba or ciliates can't get into those interterrestrial layers and can't actually break down that carbon inside those interterrestrial layers. Soil usually has about 250 kilograms of dry matter per hectare as fungi, depending on the soil, very much depending on the health of the soil, which it actually equates to about 3 kilometers per gram of actually the hyphae of the fungi. Fungi play a massive role in soils, especially in well aerated soils and soils of low pH. And then bacterial cells, they can be anywhere from 10 to the 10 to 10 to the 12 bacterial cells per gram of soil. And these also play a massive role in the soil. Then we have things like columella and mites and nematodes, but they're actually mass-wise, they're a lot less than the fungal and the bacterial biomass in the soil. And so these are amazing structures in the soil, and in fact, often the soil microbial biomass weight of the soil. So what's actually underground, if you can think of 1 hectare of ground or 1 hectare of land, the weight of the soil microbial biomass, what's living in the soil, is about a cow's worth on the top. So what's underneath is about a cow's worth of weight on the top. It can be up to like 650 to a ton of biomass that's in the soil itself. So just to give you some idea of that. So some of you have just come back from lunch or from praying. Maybe you need a small vision exercise here. And this is often what I want you would like to do. Is what we usually do is we close our eyes and we pretend we're in the soil. So you have to you have to choose which element you want to be, or which organism you want to be. Do you want to be a fungi? Do you want to be a bacteria? Do you want to be a nematode, or do you want to be a soil mite in the soil, or do you want to be one of the algae or one of the protists in the soil? So the soil mites tend to eat everything, so they're moving around. The bacteria tend to be static. Everything has to come to the bacteria. The fungi are a bit more mobile because they have their fungal network, so they can go all over the place. And the plants, again, they can go all over the place. So we'll do this vision. It's good to shut your eyes, don't fall asleep. And just so you think of what you are in the soil, shut your eyes, think of what your organism is. Have a look around you in the soil and find out where you are in the soil, where are you living in the soil. Work out what restrains you, what can't you get, whether is it water that you can't get, is it nutrition you can't get, what is really restricting you in the soil. Now I want you to think about what is your nutrition, what resources do you require? Do you need soil carbon? Do you need to eat other fungi? What is it? Where do you get your resources from? Do you get them from the plants, from the above ground material, or are you just opportunistic, like a bacteria or something, that the moment there's a burst of resources available, you just go in and actually start munching up those resources? Then I want you to think about what happens when the temperature increases. What happens to your processes, to your enzymatic processes? Obviously, in the soil, and the soil enzymatic processes, these biological enzymatic processes, are what drives most of the soil processes. And this can increase the rate of chemical processes by up to 10 to the 17, and that's the distance between the Earth and the Moon. So if you had a person standing on the Earth, there's the number of people that can be between the Earth and the Moon. So those enzymatic processes are so important. So think about your enzymatic processes. Say, as I warm the soil from say 22 degrees or whatever to 24 degrees, how would your enzymatic processes work? Now I want you to think, still having your eyes shut. Now I want you to look around again. Think about who would eat you. Where are who are your predators? But what's controlling you in terms of your growth? Why can't you grow so much? Is it because you have got some top-down grazing from things like nematodes or mites in the soil? Are they sucking you up as you're trying to break down some organic matter? So who is it that's really eating you up in the soil? So just have a think about that. Look around you again, look at the soil, look at the sand particles compared to the size of the clay particles. Look at the size of the silt particles, really about that size. And think about how it is if it's a dry day and if it's a wet day. In a wet environment, what are the differences? Why is it so much easier to get around? Is it because we've got all these layers of water that we can move about in, say if we're a thiliate or a protist, for example? And then I want you to think about what happens if it's a dry event. What happens if we run out of water suddenly? What do you do? How do you cope with that process? Yeah. Okay. And now you can open your eyes again. So I just introduce you to the world of soil. Sometimes it's really nice to do it in the dark and really to have a good vision of it. I think it's really nice to think about this way and to do it this way. So as I said before, so we have all these different processes, and really the main thing is that these different soil microbial biomass changes the very long, so we have lots of in the soil organic carbon or the soil organic matter, we have lots of very long chained polymers, very complex things like lignins, like carbohydrates in the soil. And it's a bit like the human gut, that those long chained carbons and long chained polymers have to be or need to be broken down. If they're broken down, they release energy. And that's what those organisms in the soil are using. So that's the process we call mineralization, that breakdown of that soil long chain organic matter into short chain organic matter and carbon dioxide. It's released as carbon dioxide into the atmosphere. And that's all done. Most of that process, as I said before, about 90% of that process is done by the soil microbial biomass. Obviously, the soil microfauna and macrofauna play some role, but they tend to play more of a role of they play the role of breaking down that initial organic matter into fragments to make it a bit smaller, so they can actually increase the rate. So I think what we've done some studies with like labeled litters in the field in forest systems, and what we've seen is that where we've actually had litters in bags with large pore sizes or small pore sizes, so big gaps or small gaps, that allowed the macro and the microfauna, the mesofauna in. So the mesofauna are things like the columella, the nematodes, etc., and the mites. And what we found was there was about a 10% difference between the decomposition rates between the ones that were allowed in, where the mesofauna were allowed in, and the ones where they weren't. And that was really quite an eye-opener, as 90% of the processes were really mediated by the fungi, the bacteria, the soil. So I just really want to stress that's why they're so important. And the fungi and the bacteria also make up, as I said before, about 5% of the carbon in the soil. So they're a big part of that carbon cycle. And they're consistently turning over. They're very rapidly turning over every day. It seems like that we've just recently done some studies again in Chile, and it seems like every day is about 2 days that they completely renew the carbon that they have. So it's very, very quick processes that microbial biomass pool is turning over very, very rapidly. So it used to be that we thought that a lot of the carbon was coming from leaf litter. That was the old paradigm, that we thought, carbon, soil organic carbon basically comes straight from leaf litter and just all the stuff that falls on top. But what we've realized in the past, I would say 5 to 10 years, is that actually vast amounts of the carbon comes from root exudates and roots itself in the soil. So root exudates, in the past, we didn't believe that plants, I remember having many conversations where people said, oh no, plants wouldn't be so daft to give away all their carbon and things like this. They're just far too efficient. But the nice thing is that we've proved whether they do it on purpose or whether it's an intentional thing, we will never probably know. Clearly plants aren't sentient beings, and whether they're doing it on purpose, we'll never know. But what we do see is that plants that give large amount of root exudates, so what happens is the plant takes up the CO2 from the atmosphere, that converts it into sugars. And the trouble is, in many parts of the world, there's excess carbon. There are masses of carbon available, especially if the plant's doing well, if the plant's at the top of the canopy. And because there's so much carbon, often the plant will lack nutrients. So what it will do is trade nutrients for carbon. It will supply mycorrhizal fungi and other fungi with carbon, bacteria with carbon, and mine nutrients. It will mine phosphorus, it will mine nitrogen. And now we believe that this pump is so effective and so ubiquitous, and we really can see this. We've used stable isotopes to do this. So when we use stable isotopes, what we do is we enclose the plant in a plastic bag or in a chamber, and we add a 13C labeled isotope. So an isotope is basically a big fat molecule. It has an extra neutron in its nucleus, And so it acts chemically almost identically to a normal carbon atom. Anyway, with 1% of all carbon atoms are actually 13 C atoms rather than C12 atoms. So we know they're completely safe because we have 1% of them in our bodies anyway. But what we can do is we can actually buy carbon dioxide with 99% of their atoms that are 13 C atoms. And this is a really huge amount. And this acts like a label. It acts like adding a red ink into the plant, and we can actually just follow that ink throughout all the different plant parts. We can follow it into the root exudates, we can follow it into the CO2, we can follow it into the microorganisms, and we can follow it into the enzymes, etc. And these tools, these stable isotope tools, have allowed us to actually really understand these cycles and these processes in the plants. And what it has really shown us is really this pump is so important in building up organic matter. And again, one of the reasons being is that the fungi that are often associated with the plants, the mycorrhizal fungi, they're exchanging the whole time, exchanging nitrogen and phosphorus for carbon, and they're exploring the whole soil. They're mining all over the place for soil, for nutrients. And so they're going into all the interstices, they're going into those layers of the carbon. They're having little mine through. They might not find anything. They might die there. And when they die there, they leave that carbon. They're leaving layers of carbon from their hyphae within the minerals of the clay, the fractions, or they're just leaving it on top. There's just the carbon is just left over, and that carbon, if it's within a mineral layer, because the protists or the nematodes can't get into that layer and start eating those off, can't start biting all that carbon that in there, because they can't actually get into the interstitial space. That carbon is basically just stays in the soil, and it stays for a very long time. And this is what we call our mineral associated organic matter, or our mineral associated carbon. So it's very, very stable. Also, there's a lot of sugars released, and the bacteria will take those up. I mean, but they tend to be fairly rapidly turned over in the soil. We really believe that this fungal bacterial pump is probably more dominated by the fungi than the bacteria, although the fungi also leave that necromass, that dead material, behind, and the bacteria also do. So it's really been turned on its head, the whole concept of how soil carbon builds up in the soil over the past years. Also, it pushes in the past, we always thought about the plant, the quality of the plant material, and how fast it broke down and everything like that. Now we tend to think more about the structure of the soil, the amount of carbon going in. The quality still has a big role, as we'll see in a minute. It still plays a big role, but the temperature, the environment, and that sort of thing, and how the microbial biomass in those soils, and how they influence the breakdown of the organic matter. You have to tell me how long I've been going, and so when maybe we try and give a break after about half an hour. I so do you know how long I've been going so far?
30 minutes around.
Around 30 minutes. Okay, I can
Yes.
put my stopwatch on actually.
We still have.
I still have 70 minutes to go, do I? Yeah. Okay. So we're going to talk a bit about what can we do to increase soil carbon and improve soil health. There's a number of things that we can do. As I said before, one of the problems is, I think, really in modern agriculture, and well, especially here in Europe, we've really, I mean, because nitrogen fertilizer really boosted growth so well and above ground biomass, we've forgotten that the soil actually needs a hell of a lot of carbon. The soil, for those microbial processes that I've just described, need carbon. So we've been adding nitrogen, but although the plants have added carbon themselves, we've added very little carbon compared to what they were used to compared to how they used to have so much carbon inputs. We've only left the minimal root material in the system. We haven't left residues on the field. We've always had this idea of clean concept and clean fields, etc., which has meant that many fields are very carbon limited. And the problem is once they become carbon limited, they become limited in microbial biomass, and that microbial biomass is really what's doing most of the work in the soil. It's turning over all those. And so the problem is that at one point we have this collapse in the soil health because there's so little microbial. It's a bit like your microbiome. There is a bit of a microbial desert in the soil. So how can we actually increase the soil carbon without, I mean, we don't have to reduce yields. We can actually increase soil carbon without reducing yields. So one thing is cover crops or intercrops and continuous soil cover. So cover crops here in Europe tend to be put in between different cropping cycles. So we have, say, a wheat, and then we'd put a cover crop in so the wheat would go till about June, and then we would plant up a cover crop, say in June, and then that would run to say March the next year, where we'd put a maize crop in. And these are usually, the nice thing about cover crops is they usually we don't put fertilizer on them. They can take up all the excess nutrients in the soil. They take up quite a lot of water, it must be said, but they put a hell of a lot of carbon. We've worked out that they put about a ton of carbon per hectare in at least below ground biomass in terms of root carbon into the soil. We haven't actually done the rhizodeposition calculations yet, but we see that root carbon, so just pure amount of root carbon going into the soil, is about a ton per hectare at the moment. We can also put intercrops in. That's where we grow plants with. So we grow our main crop, say, with an under crop of, say, pea or something. So that will often be done with things like maize grain. That an intercrop will be sown as the maize becomes a bit later in the harvest, and this will actually also increase the amount of carbon going in, because you have no bare period on the soil. And actually, this whole idea of continuous soil cover is really important, especially in areas of high erosion, etc. And I mean, in Indonesia, for example, I know you have a lot of continuous cropping of rice, for example, but for things like you can see here in the oil plantation, you've got mucuna cover. So this is quite an interesting, mucuna being a nitrogen fixing plant and being quite a big input into the system in terms of nitrogen. So the next one is rotation and diversification. The other thing about cover crops is they provide like habitats for bees and for different positive insects, basically, so beneficial insects. And this actually increases the biodiversity as a whole. So the nice thing is the more insects you have, probably the greater the bird population. The greater bird population you have, in some cases, I mean, it depends, that tends to keep the sort of pest levels down, for example. So these are all positive trade-offs in terms of, as long as they're not eating your crops, they're positive trade-offs in terms of biodiversity as well. The next one is rotation and diversification. Obviously, the other thing, the rotation will, as you rotate the crop, you have very different amounts of carbon going in, and you have different sources of carbon. So so the microbial biomass has to adapt to a different type of carbon. This is also the case in cover crops. The more diverse, it seems like the more diverse the crops you have, the more carbon that will be stored in the soil, because of the fact that the microbial biomass has to adapt to that soil carbon. It has to adapt to each type of sort of carbon, rather than just adapting to one, sort of like white bread or rice or whatever. It has to adapt to, the microbial biomass has to adapt to sort of like fish or whatever. It has to, so that range, it now has a range of plants that it needs to break down. And so the microbial biomass has to adapt to that. So we believe that, well, there's one theory that the more the diverse the crop is, the more the slower the breakdown rate of the carbon in the soil. Another one is agroforestry. Actually, I was recently in Indonesia, and especially in Lombok. I saw really quite a lot of agroforestry in the rice fields. So agroforestry is basically growing rice with, or growing any crop with the tree crop as an alley crop, or as a lining crop, or even as a marginal crop. And obviously this provides, the nice thing is that the amount of carbon provided by the tree in the soil is huge often. It really exceeds those of cropping plants, but it's a bit more, especially in the root biomass, is really high. It can also provide, it obviously provides sort of habitats for things like birds and owls and all that sort of, and insects. But it also provides protection, but often shade protection as well, and also wind protection if you have your alley crop set up the right way. Another one is no-till. It's still quite controversial in whether no-till really does increase soil organic carbon. But what no-till does do, and we know that really well, is no-till really protects against erosion. It's really, and so those real extreme events. And so even if it doesn't protect against it doesn't build organic carbon in the classical way, obviously very build of organic carbon. What it does do, it means when there are those really non-predictable events, that organic carbon stays where it should be, that soil stays where it should be, because it really does reduce erosion. So in soils that are really very prone to erosion, that no-till is really, it has got a benefit. The next one is biochar. I don't know how many of you have heard of biochar. I've recently saw a video where they had all these Italians saying, "What do you know what biochar is? Does anybody know what biochar is?" They're all going, "No, no, no." So it would be interesting to see how many of you knew what biochar was. But we'll see that afterwards, maybe in the chat, if you can say whether you've heard of biochar before. Biochar is basically is a material that we pyrolyze. Is any organic material that's pyrolyzed. So that pyrolysis means that it's heated without oxygen. So if we combust something, we would add oxygen, and if we add oxygen, we get CO2 from the process of the combustion. From the oxygen and the carbon coming together, we get carbon dioxide and a lot of heat. With biochar production, or with pyrolysis, we add no oxygen, but we get a lot of, and we have to heat the process slightly, we have to put some energy in, but then you get energy out. So you get methane out, and you get hydrogen out, and also you get what you and CO, carbon monoxide. But you also get, so you can, that heat is produced, so you can have a heat source, but you also get a very high carbon product left. About half of the usually 10 to half of the product remains carbon rich, so it's usually about 80% carbon, and it's like a bit like burnt, probably burnt toast means nothing to you guys. So it's just like very black, it's very, very dark, and it's still rich in carbon. As ash, when you incinerate something, or when you combust something, you only get ash left because all the carbon disappears. With pyrolysis, you get a lot of carbon left. And what we've seen is that when we add that carbon to soil, or that biochar carbon to soil, we can add it and increase the amount of carbon in the soil, but it doesn't necessarily it increases the pH, and has all these other positive effects, and I'll talk a bit about that later. Other things we can do is we can add compost. I mean, obviously, if there's composts available and organic material available, or we can add EOMs, which stands for external organic matters. These could be like manures, or they can be food waste, composted, etc., etc. The other thing is we can reduce or eliminate pesticides by using novel strategies such as sterile insect technique, such as increasing the amount of beneficial insects in the system, and using really sort of stringent pest management, integrated pest management programs. And the last one is the inclusion of livestock, which is really the sort of one of the strengths of regenerative farming. And again, in Indonesia, I saw a lot of integration of livestock in the oil palm system, but I think, again, that could be one area where we could really expand and really maximize the management power of inclusion of livestock, because there's real potential to really manage that very well, and to really make that system very profitable in terms of livestock management, and also a bit more sustainable for the future, basically. So let's go more onto their soil health indicators. Soil health is a really difficult thing to define. I mean, we all know what a healthy soil is. If we pick up a soil and it's crumbly, it's got a really nice structure, it smells nice, and it's soil, we know it's a really healthy soil. As if we pick up a soil that's sort of like, that has no organic matter, is very light in colour, it has no structure, we know that it's quite a degraded soil. So, but how do you define that? That's the tricky bit. How do we, because we need to measure these things, and we need to define these things. And so we have a number of indicators, what I would call indicators, that we need to measure soil health, to actually put values onto these. And these come from the physical, they can be biological, or they can be chemical. So they're all the different types, and that reflects the different processes in soil that are going on in the whole time. Physical processes and chemical and biological processes. This is why soil is apparently its most difficult thing to model. 1 centimetre cubed of soil is the most difficult thing to model in the world, apparently, because all these different processes are going on at the same time. So indicators. So some of the indicators of soil health are things like bulk density. Obviously, if we have higher organic matter in the soil, and we have more aggregation, and we have higher amounts of pore space, etc., then we have a lower bulk density. Sorry, so lower bulk density is a really good indicator of soil health. Another one is aggregate stability. Everyone knows that a nice soil is usually quite friable. It's usually quite dark, which the dark is the organic matter in the soil, and it has a nice structure. It has little sort of like aggregates, basically little pieces of soil that are all meshed together. And the reason they're meshed together, those small amounts of those aggregates are meshed together, is because there's so much microbial activity, and those microbes the whole time, they're pumping out enzymes, they're pumping out glucans and different sort of like different gluing structures that keeps the soil together and keeps those aggregates together. And the beauty of those aggregates is those aggregates are really quite stable, and they tend to, if there's a rain event, they don't just wash away because they're so glued together. They tend to allow good infiltration because they're aggregates. If you have aggregates rather than single particles, for example, you have much better infiltration because you have a lot more pore space, larger pore spaces. Without losing, it's not like sand is obviously water infiltration into a sand is much better than into a clay. But if you have a clay with good aggregate stability, you can have also good water infiltration, or a clay with a high aggregate strength. You can have that good infiltration. And so another one of those measures that we measure, physical indicator of soil health, is infiltration. A third one is water holding capacity. And then subsurface or surface hardness. This is just basically how strong, or how much the roots have to work to get into the soil. And then we have some chemical indicators. pH is obviously one. Low pH is really detrimental not only to plant growth but also to the breakdown of organic matter. And this is why we get things like peat bogs, etc., is because they're so low pH that the organic matter stays there basically. But that's not particularly good for production. So pHs are really important. And then soil organic carbon and nutrient retention. Obviously, the more organic matter we have in the soil, is really the nutrient retention is also higher because we have more cation exchange sites, etc. And then soil, the microbial diversity at the end is also an important thing. So some of the biological indicators of soil biodiversity, again, microbial activity. So how many microbes are actually in the soil, how much is there. So some of this we can either actually measure the sort of respiration rate of the soil, I would say with some caveats. If we measure the respiration rate of the soil, what we've got to take into consideration is the temperature at which we're measuring the respiration, and also the moisture content we're measuring the respiration, and also the differences in the soil. Different soils will have different ideal moisture contents, etc. So that makes it complex. So sometimes maybe it would be easier to measure something like soil or enzyme activity. Again, we have to take into consideration temperature and moisture, or soil organic matter decomposition over a time. That will give us some idea of a healthy soil. And again, soil respiration. But all these things are really important. They really show how healthy the soil, what the population of microbial biomass is in the soil. And what we've got to remember, that key parameters of indicators, they need to be, if we're devising a system to measure soil health, we need to make sure that these parameters are measurable, that we can measure them, they're robust, that we can use them. Like if I use them here in Vienna, that you use them there in Jakarta, or if somebody uses them in Sydney, that those methods will give approximately the same. They should give the same result, basically. So that we can do cross comparisons, of treatments. Anything that's rapid, reliable, and repeatable, it's all about simplicity. Anything that we need we can have technical methods, but they have to be, the more complex the methods become, the harder it is, or the more mistakes that can be made, and there's the more sort of like there's the greater opportunity for error. And so really many of these methods, they need to be rapid. Often the less steps you have in a method, the less likelihood there is for error. And they need to be repeatable. We need to be able to run them again and again. And the final thing is they really need to be implementable. It's really important that we can actually do many of these things, because we know that many labs don't have sophisticated equipment. And to be quite honest, I've always worked in a lab with many mass spectrometers, but we haven't always had the budget for the sophisticated equipment to measure things like nitrogen or ammonium. So we need to have methods that are easy to access, basically, so that they're democratic. So one of the ones, as I said before, is bulk density. Bulk density is a really simple measure to do. We use these basic rings and run a bulk density measurement. And bulk density has a really strong, obviously, as the increase in bulk density, that's as you increase the organic matter in the soil, that you do increase yield, because basically the plants aren't putting the energy into sort of like fighting against that strong soil, fighting their roots down, putting energy into sort of like into penetrating the soil. They're putting their energy into the plants and to the yield. Also, the lower the bulk density, lower weight, more pore space, basically. And the higher bulk density, higher weight, less pore space. So that we see that yeah, basically if we have a low bulk density, there's the basically the soil is more fluffy, and that we can actually attribute that as I said before, the roots and everything can penetrate so much more easier. And you can see here that as we increase organic matter, we can see a big decrease in bulk density. So we can go from like 1.5 right down to, I mean, I know 40% is really quite high organic matter. These are obviously, but you can see that there's quite a big range. We can even work with this is on the right down on the right hand side. There's a big range we can work with to start with. The bulk density and organic matter have a really big. There's a really big correlation between the two. So bulk density is again an organic matter. And organic matter is basically carbon. I mean, at the end of the day, when we add organic matter, we add some nitrogen. Obviously, we add nitrogen in a similar amount. But when we add organic matter to soil, we're talking about carbon. As I said before, one of the aggregate stability is also a really nice measure. Is a nice, but actually measuring aggregate stability. I don't know. Measuring aggregates, it's not so easy. It's not such an easy measure. We can do some very simple methods, but I mean, simple methods that are repeatable, reliable. We can do field demonstrations where we take clod or take an aggregate and put it into water, in a net, and see how much of it comes off, how much the aggregate comes off. This is like a slaking test. This is the simplest test, the one up on the top right hand box. There was a really nice talk from somebody in France, where just recently in the EJP conference, where they were doing, basically they'd taken aggregates and put each aggregate into a microtiter plate and then added water and watched how the aggregate dispersed over time using a microtiter plate reader and using a camera to see how quickly they dispersed. That was quite an interesting one for looking at aggregate stability. And then we have these machines. I mean, the machine here, the Ellen Camp, the one you see in the middle, is a very simple machine. All it does is you put the soil into a small sieve and then you put the sieve up and down. The machine basically it pushes the soil up and down in the sieve, and like the non-aggregates fall to the bottom, or the unstable soil falls to the bottom, and the stable aggregates is like a wet sieving. So the stable aggregates stay on the top, and you can get a nice, and it is a really nice measure, and it's very field. It really relates to field parameters. I remember we did a student sort of like excursion with the lab, and we showed very nicely that aggregate stability was one of the only things that really related to sort of like fungal biomass in the field. So it was one of those correlative figures that we could really see that as we changed the microbial biomass, that actually aggregate stability, as we increase the amount of fungi in the soil, the aggregate stability increased. And then we can do some other more chemical tests, which are basically physical indicators, but they're biologically driven. So I was talking to you earlier about these glues and these gluons and these extracellular polysaccharides is the whole term for these things, or EPS. And we can actually measure the amount of EPS that are in the soil. That gives us also gives us an indication of aggregate stability. And these other ones, things like infiltration, there's some different techniques here. These are fairly simple, where basically you add a certain amount of water. You can either use a single ring or a double ring system, and you just measure the rate at which the water decreases in the cylinder. And what you have to do is be very careful to make sure that you're in your logarithmic phase before you put your first sample in and work out. And you just need a stopwatch. So these are really nice techniques to do in the field. There is this other this new technique, but this is more for turf grass. I think it's called Turf Tech or something. Again, it's quite a nice little instrument. It's about €600, $600 for measuring infiltration in grass. But whether it works so well on sort of agricultural fields and forestry areas, I don't know. But again, what you can see is infiltration rate goes up as we increase the soil organic carbon. That's quite clear, because soil organic carbon really acts as like a sponge. It's like it just makes the soil so much more spongy, and it will actually increase the amount of the infiltration rate because of that, because it's like it acts as a sponge. Other things like water holding capacity, and obviously there's the difference between the water holding capacity and the wilting point is somewhere between that saturation and that wilting point. And obviously, the more organic matter you have in the soil, the greater that window becomes, because you've increased your available water. And there's actually some quite nice work been done, and I have to put his name. There's some really nice work been done recently on whether you could use NEARS to actually predict the water holding capacity. And I'd point you to here, because the nice thing about NEARS is near infrared spectrometry. Nice thing about NEARS is it's a really simple technique. You just sort of point and shoot at the soil sample. And you don't need to do all these, like you don't need to measure the PF curves and anything like this. So it's quite an interesting approach, and they seem to get fairly good RMSEs and fairly good R squares for some of these for these different soils. So it's worth having a look at. Another one is soil strength, as I said before, and hardness. You can see here is a really quite hard soil, and obviously we need a pentrometer to measure these. But you can see here we've got a nice example of how roots, if we increase the bulk density of the soil, how the roots actually really find it very hard to get in and very hard to grow in those soils. Okay, so I think I've now been going for about an hour. And I think maybe we just stop for 5 minutes, and like you can have a stretch, and I'll come back in about 5 minutes. Is that okay, Andy? Because I'll go on to a slightly different subject next.
That's fine, I think.
Yeah. Okay.
Yes.
Yeah. So I've got far more slides than. So have I been talking for an hour?
Yes.
Yeah. Okay.
Thank you. Okay,
sorry,
let's take a break. No, that's fine.
Let's take a break.
Let's take a break
for 5 minutes.
for 5 minutes, I think.
Late, we can come back in 5 minutes. Yeah.
Yes.
Perfect.
Thank you so much. Yes. So we will take a break for 5 minutes. I think if you have any questions, maybe you can prepare them and save them for later. We will be waiting for Dr. Hood-Nowotny for 5 minutes, I think. Thank you.
So, yeah. So just say, Andy, when you want me to start again. When.
Yes. Thank you. Shall we have a
Okay.
question and answer session before you
Yeah.
continue the presentations?
I'll continue the presentation for probably about another 20 slides.
Okay. Shall we have now for the question and answer before you continue?
We could do.
Okay.
Yeah.
There's just maybe just one question.
Yeah.
Okay. So we will have, yes, we will have one. We would like to welcome one question from the participant if we have.
Uh-huh.
Yes. Any of the participant would like to ask Dr. Hood-Nowotny, maybe any of you about the soil carbon? Any of you, maybe?
Yes, I want to ask.
Yes, thank you. Can you say your name first, maybe?
Yes. My name is Abu Huraira and I come from Pakistan. So my question so far is that what type of biochar will be the most effective for the soil health, as there are so many various types of biochar available? So that I would like to ask so far.
Oh, yeah, that's a bit later on in the talk, and I don't know if I'll get there, but usually what we find is woody biochars are the best, but obviously that's not the best thing to use. Usually we always prefer to use like organic material that has no other purpose or no other, so things like rice husks, the insides of maize cobs, for example, coconut shells, anything with fairly dense, but is always waste stream products. We would always sort of prioritize over like primary products that could be used for something else. I mean, cassava sticks are really good, like cassava branches and everything. The other thing is it's the high temperatures really important. Like it has usually you get the best effects over 600 degrees C. So that's usually is about the level. Then you get the highest porosity. You also get the highest pH effect. I mean, biochar is really all about pH. Most of the benefits we see from biochar are because it increases the pH in low pH soils, and that then has huge impacts on not only the microbial biomass function, but also on things like the phosphorus cycle and the chemical stuff. So that's why I would recommend always go for something that doesn't have waste stream products, because then you can get them cheaply and you know that you're not doing environmental damage. In fact, you're sequestering carbon using those products, because normally they would break down within 10 years, just break down to CO2. As if you make them into biochar, they will take like 100 years probably to break down. Does that answer your question?
Yes, thank you, Professor Rebecca.
Thank you, Dr. Hood-Nowotny. If you are ready to start again.
Yeah, so should I carry back
Yes.
on or carry on a bit?
Yes, we still have 15 minutes.
Oh, it's only 15. Oh, that's a good thing.
15, yes, until 12 in Austria time.
Oh, okay, perfect. That's why I better start. Okay, so I've obviously got far too many slides, but so now I'm going to talk to you about some of the projects we're doing here in Austria, looking at soil carbon. One of them is looking at how we are using different varieties of crops to increase soil carbon, and different varieties, and we're really concentrating on the root aspect here. So here we can see that crop variety, changing crop variety is one of the things under the IPCC that has been highlighted as one of the ways of improving soil carbon. And you can see agroforestry and change in monoculture to crop diversification and perennial farming. They've all been like highlighted. But as I said before, oh, sorry, that was another one. Why we want to do this is because soil carbon, we've decided that if we can increase, I mean, most of you have probably heard of this, that if we can increase soil carbon amounts by 0.04% or 4 per mil per year, we could actually mitigate much of the carbon that's being released into the atmosphere from fossil fuels. That's not to say that we couldn't reduce the fossil fuel emissions, but it would be quite a big chunk of the fossil fuel emissions we could mitigate. And we'd also have more sustainable and more healthy soils if we did actually add soil carbon. But most of you know that adding soil carbon is never an easy process. You have to increase production to do so, and you have to get that carbon into the soil. So here are some examples. So it's all about getting that enhanced carbon storage. Here we can see getting carbon into the soil. It's not just about increasing the percentage carbon, but it's also about that carbon stock. So if we increase the percentage carbon in the soil, often we decrease the bulk density, and so we have to take that into consideration. So when we do carbon stocks, we always have to take bulk density into consideration. Here you can see one example where we've been growing different mixes. On the left-hand side, we've been growing different mixes of maize and vetch in combination, and mono, so which is maize again, and maize mono without incorporation. Here, and what we've done here is we've added different amounts of we've either incorporated the vetch. Vetch is an intercrop, so we've either incorporated the vetch or not incorporated the vetch in these mixtures, in these mixed cropping systems. And what you can see is, obviously, if we grow maize alone, sorry, if we grow maize alone, we actually get a decrease, and this is over 10 years, over 10 years, we get a decrease in the soil carbon stock. However, the vetch incorporation, as I was saying before, this above ground incorporating really didn't make that much difference. So in this system, this could possibly be an entry point for, say, an animal, so you could graze off the above ground factor. And we can also check some of these research. This is now on the right hand side. You can see we did some imaging. We did NDVI imaging of using drones, and we showed actually that the mixed vetch had the best growth, basically. And we don't know why the incorporation actually suppressed the best growth. This was in the following crop in the maize. So it's quite interesting to see that you can see these effects, but really only after 10 years. And you can really see that the carbon stocks after 10 years, even with the mono versus the mixes, that's 10 years, and it's really only about 15 tons different. That means 1.5 tons per year. It's not huge amounts of carbon going in there. So yeah, they're the sort of like 1 to 1.5 tons of carbon are the sort of differences we're making. Whether that hits this 4 per mil strategy is really quite debatable. Yeah. So but these types of experiments really made us realize that we should be concentrating on root carbon, because we could see that above ground carbon wasn't having that much impact. And there's quite a lot of other information why root carbon is so important, especially in agricultural systems. 90% of all the carbon inputs into the soil are root carbon. The root carbon is, because it's got a higher C/N ratio, tends to stay longer in the soil, so it's got a higher residence time. And it really is, root carbon is what really creates a lot of the long-term storage in the soil. And the amount of root carbon is dependent, obviously, on the crop growth. I mean, if you have higher crop growth, you usually have higher root carbon. the pedoclimatic condition. Been doing a project called EJP Soil, and in fact we've been doing more than 2 projects. Can you still hear me? Because it's saying my internet's unstable. A number of projects within the EJP Soil looking at root carbon, inputs from root carbon. So the rationale here is that we have different varieties of wheat grown, and what we wanted to look at is whether different varieties have different root carbon inputs. So whether we can increase the carbon input from soils by literally selecting for specific varieties across Europe. And the rationale here would be that this would be quite an easy to implement strategy for Europe, because the European Commission anyway, or the European Parliament, they define a certain number of varieties they have like a list that you're meant to grow. So if we could find a variety that's really high in root carbon accumulation, that's also high in yield, or at least reasonable, we could actually use that quite to increase soil carbon across Europe. So how did we do this? Well, luckily there was another project looking at different varieties across Europe, and we basically went to them and said, "Oh, can we join your experiment?" And they were really very happy for us to join. And then so in the end we had 16 varieties at 14 sites, and then we did the hard work. Well, I didn't do the hard work because I was actually in Indonesia most of the time, but they did the hard work. But what they did, so sorry, I just skip here. So what are the forms of root carbon inputs we can have into the soils? We can have primary coarse roots, which are easy to get out. We have the lateral fine roots that are a bit more tricky to get out of the soil. We have to wash them out of the soil. And then we have rhizodeposits. These are this carbon that I talked about earlier, the sugars, the exudates and the sloughing off of cells, etc. And this is the one that's really hard to measure. But so what we did is we went around these 11 sites across Europe, or the team went around Europe, and they used these big cores you see in the top right-hand corner to drill down into the soil and take a number of soil cores and then pull those soil cores up. It's all hydraulically run and everything. And then once we'd got the core, you can see at the bottom left-hand corner, we would split that core up into 15, 30, 50, and 120. And then we would wash the soil. So we'd hand pick out the top layer. We'd hand pick out all the roots, all the sort of like recoverable root fraction, basically, all the macro roots. And then after that, we would wash the soil. We'd wash each one of those cores and wash out the roots. A very, very tedious process. I've had a PhD student doing this. It's taken her 6 months to do cores from 11 sites. But what you see is we've got some, so the root biomass here is showing from the different countries that there actually is quite large differences between countries, but often this is really dependent on the soil. And what you see really is that actually the majority of the roots, as we suspected, are in the top 15 centimetres. In the second 30 centimetres, note that the change in the axis, because actually in the second 30 centimetres, there's really very, very little carbon. So, I mean, in so as we go down, we see there's less and less root carbon, but that which was clear. So we can use the 80-20 rule, that 80% of the carbon is actually in the top 20 centimetres, and that's really what we're really interested in, and that's what we're interested in increasing. The idea of getting the subsoil, trying to improve subsoil carbon, is that carbon, because it's cooler down in the subsoil and there's less oxygen, etc., that carbon actually stays longer. So whether we can actually select for plants or select for varieties that access or have quite extensive subsoil carbon is also quite interesting for us. Also, the other thing is, obviously, further down the subsoil, there's obviously more water available as well. So it means that these plants might be more drought resistant. So we're working on that aspect as well. Here you can see the root biomass, and this is when it comes to the different varieties. You can see, so the left is the environment or the different countries, and the right is the different varieties. And you can see that we do have some varieties that consistently come out slightly higher in terms of root carbon. The thing is, what we did find is that we found site variability was much higher than the variety variability, which to some extent we expected. But what we can say is that it looks like we can actually select for specific varieties that will give us a higher root carbon overall, or give us a higher below ground carbon. So that's quite an interesting fact. I won't go into the video, maybe at the end. And so, I mean, carbon measurements, a lot of it we do with, we do, and I'll show you how, but these macro carbons, here we're doing the macro roots. Here we're measuring the macro roots of maize. Again, it's really hard work. We do a lot of digging. We dig out like a large circle of the root for the maize, and then we wash it. We have to cut it and wash it and and then determine the amount of biomass. But here we are also doing what we call shovelomics, looking at whether, here in this experiment, we were looking at different external organic matters, things such as biochar or compost, and seeing whether there was a difference. And here we can see the things like the biochar. We actually thought that the biochar would increase the amount of root growth, but it seemed not to, which we were quite surprised about. Obviously, NPK, so fertilizer against control, increased root growth, probably because you've got higher root growth anyway, because you've got higher plant growth. What really amazed us was, in fact, that the biodigestate clearly increased root growth much higher, which is biodigest is coming from a biogas plant, and then that biogas plant material is actually added back to the, after the biogas has been generated, it's added back to the soil. And that actually had a really high root carbon. So we're starting to show some management effects. How we're looking at riser deposition in the soil, you can see here, we've gone from a very simple approach. So it's simple and not so simple in some degrees because we're using stable isotopes, but for us, that's our sort of like our key area. We've added, what we do is, as I said to you before, that the C13 is like the heavy carbon atom, which is available 1% in the atmosphere. We can add 99% CO2. So with 99% of the atoms in that carbon dioxide are actually C13 atoms. And what we do is we do it by putting a bag over the plant. These are just these vacuum bags you use to store clothes. In Austria, we have winter clothes and summer clothes, and we store our winter clothes in vacuum bags that are see-through, that are gas tight, and we put them around like the cylinder at the bottom, and then we can inject 13 CO2 into the material, and then we can follow that carbon. So obviously the plant photosynthesis synthesizes all that carbon dioxide that's in the bag. We chase it with an unlabeled carbon dioxide. We can actually work out where all that carbon is going and measure how much of that actually. So what we do is we then take out the root cause, we wash the soil, we take out all the roots that we can, and we measure the C13 in the soil itself, and that gives us an idea of the rhizodeposition. And we've just been, this is all work in progress with us. I mean, it's just ongoing at the moment. And on Friday, for example, we found out that we've got really quite high 13C values in our soil. So we've got plus 30 per mil, as normally it would be minus 29. So we've got a really nice big difference in the soil, even though there's no roots. Obviously all that carbon is coming from the rhizodeposition in the soil, and it's a really nice method. And we've done that across 4 sites in Europe. Don't know why we've got that. So here, these are some of the measurement methods we use for measuring soil carbon. So we use like the basic classical sort of like more chemical methods, such as the Walkley Black, or I can't remember the other one, but loss on ignition or whatever. Then we use an elemental analyzer, basically, which combust. You take a soil sample, you put it into a small tin cup, you combust the sample at very, very high temperature. It goes up to 1,400 degrees. Everything becomes gas, and then you measure the CO2 gas that comes off. That's the sort of standard method we use here. We have this linked to an isotope ratio mass spectrometer, which allows us to measure the C13. But however, there's a lot more simple techniques coming along for measuring carbon, such as the NIRS system. But these are all proxy measurements. You get good organic carbon proxy measurements, but they're probably good enough for doing soil organic carbon measurements at a large scale. These are just some of the methods we're using for looking at soil biodiversity, for example. So we're using more DNA-based methodologies. I'm sure you guys are as well, using DNA barcodes, etc., for looking at soil diversity, especially for the sort of macro and mesoinvertebrates. And then for decomposition, for example, another one of those really big ones that we're looking at in soils is we can use, as I said before, litter bags, straightforward litter bags, where you'll just add a residue and into a mesh bag. There's also the tea bag index. There's also an index, cotton strip index. There's various methods. We tend to use a C13 labeled material method, and then finally there's the underpants method, which is really quite interesting, where they basically bury underpants in the soil and see how well they degrade. They're always quite a nice, quite an interesting spark of conversation. So we have all these different methods, and you can see the remaining dry mass is really very different between different species, especially of plants. But also, if you use the same species of plants in different areas, you can see that the decomposition rates of different soils will change, and that will give you an idea of how well the soils or how good the soils are at decomposition, and so how healthy they are. And then the last, respiration measurements. We have all these different measurements for doing respiration. We have what's called we have the LICOR method, which is more of a chamber method, a static chamber method. We have the micro-resp at the top, which is a nice simple method, which means that you can control moisture and temperature. And basically what happens there is you add the soil in the chamber at the bottom of the plate, and then you put a plate with an agar gel on the top, and the gel will change colour depending on how much CO2 is released. So that's also another nice one to do. We can use CO2 sensors that you see on the left-hand side just into kilner jars. We use a lot of kilner jars in our work, and just measure the increase in CO2 over time, etc. Again, a good measure of soil health, but again, very careful about the moisture contents and comparing things with different moisture contents and different temperatures, but often we'll see very big effects. And the last one I'll talk about is enzyme activity. As I said before, enzymes have a massive role in how they control the soil processes, specifically of mineralization, nitrification, all the major processes, phosphorylation, for example, all the major processes in soil. And we can measure them using various chemical techniques based on these microtiter plate or microplate readers. We basically either add the substrate with a fluorescent conjugate into the soil and actually see how much of the fluorescent, how much the soil can break off that fluorescent conjugate and measure the fluorescence, or we just measure the product of the enzyme, such as if we're doing a urease measurement. So we're trying to measure urease in the soil, we'd add a urea and measure how much ammonia is released, for example. And I think with that, I should finish. I have actually got another 32 slides, but that might be for another day.
Yes, I'm so sorry. The time is
No,
up,
don't worry.
actually. Yeah.
I can upload all the slides. It's no problem. So maybe anybody who's interested in biochar and can.
Okay.
Yeah.
Okay. Thank you. Unfortunately, the time is up right now.
No,
Mr.
it's with me.
Hood-Nowotny.
I don't always forget that I speak too much.
No, that's fine. That's fine. It was interesting talks, I think, about many things, about change, about the soil carbon, even management practices affecting the soil carbon. Yes, I have some notes here actually. Unfortunately, the time is up right now. Can still we have one question from the participants, or I think Miss MC, can we still have time?
Yeah, I still have time. Don't worry. It's raining still.
No? Okay.
Oh, okay.
Okay, thank you so much. Yes, thank you so
thank
much
you.
for the presentation, Dr. Hood-Nowotny. I think the participants have many questions, I think. So maybe they can send you email about them if you are not,
Yeah.
if you're okay with that.
Maybe you collect them and
Okay, that's
and then
nice. I
send
think.
me one email. That might be the easiest.
Okay. Yeah, there will be 50 emails to you.
Yeah.
Yeah, yes.
That's the last thing I want on a Monday morning. yeah. If you
Again,
collect questions,
yes.
that'd be fine. Yeah. And so they can write them in the chat.
Okay.
Yeah.
Again, thank you so much for the presentation, for the talks about the soil carbon. Before we end this session, I think the organizer have certificate of appreciation to you.
Well, thank you. Well, thank you for giving me the opportunity.
No, this is a good opportunity for us too, actually, to listen to your presentations. Ms. MC, shall we give the certificate to Dr. Hood-Nowotny now?
Okay, thank you so much. Oh, ada yang YouTube ya? Check. Thank you so much, Rebecca Hood-Nowotny, Ph.D., for delightful information in the second lecture session with the topic carbon measurement for mitigating climate change. We would like to give the appreciation certificate to Rebecca Hood-Nowotny, Ph.D. by Symbolize.
Thank you.
We would like to give a big applause to Ms. Rebecca. Thank you so much for useful material. And we also say thank you to Ahdiar Fikri Maulana PhD as a moderator that has led this discussion in the second session. And the certificate of the moderator will be given by Symbolize. Could we give a big applause to the moderator today? Thank you.
Thank you.
With the session of appreciation certificate already implemented, then the second mature of the summer course has ended. We also remind you to fill the attendance form. And for online participant, the form will be given in the chat section. You may stop the recording for the second session. Thank you.
Thank you.